Hi, in this video we shall solve a problem on magnetic force on a semicircular loop. The question says, consider a closed semicircular loop lying in the XY plane. This is XY plane, carrying a current I counterclockwise as shown. A uniform magnetic field is applied in the XY direction. The equation says find the magnetic force on the straight segment and on the semicircular arc. So this is the straight segment and this is the semicircular arc. If this is your first time of joining us, do well to subscribe for more updates like this. Let's get started. Now look at this. These are the magnetic field lines. We can write the force as F equals ILB. Now, if we want to consider the force, the magnetic force on this straight segment, let's define the length from here to here. Of course, from here to here is R, so L will be 2 times what? R. 2 times R. Of course, this is a semicircle. From here to here is the what? The radius. So we can call the force on this straight segment as F1, so that we can write that F1 equals, of course, force is a vector, we represent it this way. F1 equals IL what? B. And now, since we are looking at the segment, straight segment, we can say I standing for current times the length is 2R times what? I. Of course, we can decide to look at this this problem from this angle. So if we take our point here, this is Y and this is X, this will be positive X and this will be what? Positive Y. So we can say that this is I and this is what? J. So we can say 2R. Let us define the direction. We can call this I. This is I times the B. Now the magnetic field B, we can represent it as B. Then since it is on the Y direction, we can write it as what? J. So we can now have something like this: 2IR B. If you cross I and J, you get what? You get K. So the force on the straight segment is 2IRBK. 2IRBK. So of course this is the unit vector. This is the unit vector. So this is how to find the force on the straight segment. So how do we find the force on the semicircular arc? So when we find the force on the semicircular arc and we add it to the force on this straight segment, we now notice that the net force, the net magnetic force on this semicircular loop is 0. So similarly, we know that force is ILB, magnetic force. So we can call the force on this semicircular arc as what? F2. So for us to get this, let us define an infinitesimal length and call it the L. Let this be what? The L. Such that we have this configuration. So this will look like this. So this is the L, this is the theta, this is angle 90 degrees here, and this is R. So we can say opposite upon hypotenuse is sine. So we can say sine the theta equals opposite upon hypotenuse, such that the L is r sine d theta. So the infinitesimal length here now, of course, we want to define an infinitesimal length. So if we define an infinitesimal length, we also define an infinitesimal force. Infinitesimal force now in this case will be I, the L, then times B, where the L is r sine what? The theta. This is theta. So if this length happens to be a displacement or the displacement of the current, we can write it as the L, this is sine of direction, equals r. Okay, of course, we can say that sine d theta is approximately equal to theta, or is approximately equal to the theta when theta is very small. So we can write that the L, this is a vector now, if we take it as displacement, equals what? The theta. So, and we can write a unit vector in the direction of theta as this. This is a unit vector in the direction of theta. So this unit vector in the direction of theta can be given as, this is unit vector in the direction of theta, it can be given as minus sine theta I plus cos theta j. So if we take that, the unit vector in the direction of theta is this, the elemental change in the displacement in length, call it displacement in this case, will be r. Then we have minus sine theta I plus cos theta j. So this is the infinitesimal change in the displacement. So having found the infinitesimal change in the displacement, we can now find the infinitesimal change in the force. And this is the force on the semicircular arc or loop. So we write that the F2 equals, this is I, the L is R, the theta minus sine theta I plus cos theta j times B, the magnitude is B. Okay, we can write the direction as J because it is along the y-axis. If you cross this, you have finally that this is minus I BR sine theta the theta, then you have unit vector in the direction of what? K. To find the force on this semicircular arc, we have to integrate this. So we have that F2, to find F2, we integrate this. This is the F2 in the limit of 0 to what? Pi. In the limit of 0 to pi. So this is, because this is a semicircle. So you have 0 to what? To pi. And we have the F2 as, this is minus I BR sine theta the theta what? K. Now these are constants. So we have that F2 equals minus I BR, then you have K, integral from 0 to pi of sine theta what? the theta. So if you perform this integration, you have that this is minus 2I BR, then this is the unit vector. So this is what? F2. So this is the force on this semicircular arc. So if we now want to find the net magnetic force on this semicircular arc plus the line segment, it will be that the net force will be F1 plus what? F2. And F1 we got it as 2IR B, then have the unit vector in direction of K, and F2 we have it as minus 2I BR, this is BR, unit vector in direction of K. Now see that this is what? 0. So the magnetic force on a semicircular loop having this straight segment is what? 0. If you have enjoyed this video, give it a like, subscribe for updates like this. This is Neselefa Academy, and we are signing out.